Hello, everyone. My name is Prajwal Aryan Imadi, and I'm part of the BSc Honors Data Science and Artificial Intelligence program at IIT Guwahati. In this video, I'll be presenting my Trimester 8 Term Project 2 submission. The title of my project is a hybrid supervised contrastive learning framework for diabetic retinopathy classification. This project explores how deep learning techniques can automatically detect diabetic retinopathy from retinal images and help support early diagnosis of eye diseases. Diabetic retinopathy, or DR, is one of the leading causes of preventable blindness worldwide. It occurs when diabetes damages the small blood vessels in the retina, which can gradually lead to vision loss. Early detection is very important because timely treatment can significantly reduce the risk of severe visual impairment. However, traditional screening methods require trained ophthalmologists and specialized equipment, which make large scale screening difficult. Deep learning and computer vision offer a promising solution by enabling automated analysis of retinal images. The main challenge in detecting diabetic retinopathy is the accurate classification of retinal images in different stages. Manual diagnosis requires expert doctors and can be time consuming. Another challenge is that medical datasets are often imbalanced, meaning some disease stages have fewer examples. Additionally, single deep learning models sometimes struggle to capture all important features in retinal images. Therefore, the goal of this project is to develop an automated deep learning system that can accurately classify diabetic retinopathy stages from retinal fundus images. The project objectives. The main objectives of this project are first to develop a hybrid deep learning architecture that combines multiple neural networks such as ConvNeXt, ResNet 101, and MobileViT. Second, to improve classification performance by combining different feature extraction methods. We use a different hybrid model for that. Third, to address class imbalance using techniques such as focal loss, and data augmentation. Finally, to improve model explainability, we use explainable AI methods such as GradCam, which visualize the regions used for the prediction. The technologies uh, and tools used for this project. This project was actually implemented using Python. The deep learning models were built using PyTorch, and Torch Vision. For development and experimentation, I used Google Colab and VS Code. Additionally, libraries such as NumPy, Pandas, Matplotlib, and Scikit-learn were used for processing and visualization and evaluation. Kaggle was really helpful for implementing the notebook ideas, for running the notebooks. Moving on to dataset, two benchmark datasets were used for training and evaluation. First is Aptos 2019, which contains retinal images of 3,662, categorized into five deep diabetic severity classes. The second dataset is Mesidor 2, which contains 1,744 retinal images with expert annotated labels. The dataset was split into 70% training, 15% validation, 15% testing to evaluate model performance. Data preprocessing. Before training the models, several preprocessing steps were applied. Images were resized to 224 by 224 pixels to match input size required by the neural networks. Contrast enhancement using CLA was applied to improve the visibility of retinal features. Additionally, augmentation techniques such as mix-up, cut mix, random cropping, and color jitter was used to improve model generalization and reduce overfitting. Moving on to the diagram, as you can see, the fundus image input is given here, and then we use pre-processing steps and train the model to make a accurate model. Then we move on to the feature detection, like what kind of feature is actually detected here, and we make a fine prediction. And the final image is presented using GradCam. so it is very clear and accurate. Moving on to deep learning models, several deep learning architectures were evaluated in this project. These include ResNet 101, ConvNeXt, MobileViT, and Swin Transformer. Each architecture captures different types of visual features. In addition, hybrid models were developed by combining multiple architectures. The final hybrid model combines ResNet 101, ConvNeXt, and MobileViT. These actually strengthen the network. The proposed hybrid architecture. The hybrid, the proposed hybrid architecture actually combines of three networks, as explained before: ConvNeXt, ResNet 101, and MobileViT. ConvNeXt captures modern convolutional spatial features. ResNet 101 extracts like deep features using residual learning, and MobileViT integrates transformer-based attention to capture global image context. Features from these three models are fused together using a weighted feature fusion mechanism. This approach allows the model to capture both local retinal lesions and global structural patterns, improving classification accuracy. The training setup. The models were trained using NVIDIA Tesla P100 GPU, which is powered by Kaggle, and training each model took like 3 to 6 hours, and the optimization process used the uh, Adam W optimizer with cosine annealing, learning rate scheduling. The optimization, like transfer learning from ImageNet pre-trained weights, was also applied to improve training efficiency. Class imbalance was addressed using focal loss and balanced sampling techniques. The results. The experimental results show that the hybrid model achieved the best performance. The best performing model was the combination of ResNet 101, ConvNeXt, and MobileViT. On the Aptos dataset, the model achieved accuracy of 93.04% and F1 score of 93.11% and precision of 93.5% and the recall of 93.04%, as shown in the table below. These results demonstrate that hybrid architectures outperform individual models. Explainable AI techniques were used to analyze how the model makes predictions. GradCam heat maps highlight important regions and retinal images. These visualizations show that the model focuses on clinical relevant areas such as retinal lesions uh, and abnormal blood vessels. This improves transparency and helps build trust in AI-based medical systems. This is the TSNE diagram used for like how the classes are like they're very imbalanced, and we use the supervised contrastive learning subcon to actually separate them and actually make a good prediction on the data. As you can see, this is the left side one is the before one, and the right side one is after the process is actually applied. This is this the experimental results actually demonstrate that hybrid models actually outperform CNN. Like the hybrid architecture actually outperforms the individual models used, as shown in the table. This was actually very helpful. The key observations here, like hybrid models capture both local and global features. As a mix of the models, actually the layers are separated using transfer learning. So the features, actually the important features are used here and there. So the hybrid model actually helped me get a higher accuracy and a good model for this. In conclusion, this project proposed a hybrid deep learning framework for diabetic retinal classification. The hybrid architectures combining ResNet 101, ConvNeXt, MobileViT achieve the best overall accuracy. The system improves classification accuracy, handles dataset imbalance, provides accurate predictions. This demonstrates the potential of deep learning systems for automated medical image analysis and early disease detection. Moving on to the future work. Future work includes training the model on large datasets such as IPACs, applying semi-supervised learning techniques, and developing lightweight models for mobile healthcare applications. These improvements could enable like it could scale AI-based retinal screening systems. Thank you.